Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I think we'll try to start again. If I'll ask all of you to sort of slowly stop the conversations and sort of slink towards your seats or other seats. Or thank you, excellent. We tried to be a little disruptive this year, and we didn't just say, oh yeah, machine learning and computer vision, and just throw you all in a room and see what happens. We tried to get some talks that are thought-provoking and maybe out of context or non-linear. You may think it's random. I like to call it non-linear, just me. But it's actually very, very interesting what we're going to hear, taking an economic look at some of these same problems we were looking at. Baby, I apologize in advance for bastarding your name. Acting this baby, the Stern School of Business, and I'm actually personally very interested to hear this. So, welcome. Thank you.
Thank you. And hello, everyone. This should work. I'm very happy to be here and introduce our work, improving local search for hotels using econometric modeling and image classification. This work has been done with Professor Anito Ghosh and Professor Panos Ipiratis. So, before we start, oftentimes we would have this sort of question: how can I find a hotel near Redmond, Microsoft headquarters, less than 1 mile away from Washington Lake, with easy access to highway exits, and also providing a good price for what it offers? So this is a very typical question usually we would ask before we go visit somewhere. And the original motivation of our work is try to help you to solve this question. So here's our research agenda. The problem is we want to locate hotels that satisfy specific criteria and offer the best value for the money. And the challenge here is currently there's no established metrics that can isolate the economic value of the location and service-based hotel characteristics. So the method we're using is we combine the econometric modeling with user-generated content data and image classification method to identify and measure important hotel characteristics. So here's the overview of what I'm going to talk today. First, I will give an introduction of the background, and then I will introduce the how we identify these hotel characteristics and how we collect the data. And after that, I will introduce our econometric-based ranking approach and how we evaluate this ranking result. And finally, I will give the conclusion and future work. So, as we just mentioned, customers like you and me, we try to identify hotels that satisfy a particular criteria. For example, the food quality or the service. So what we usually do is we search. Here is a very typical travel search engine usually we can find online. And as we can see here, usually they provide only rudimentary ranking facilities using a single criterion. For example, they sort these hotels by their name, or by their price per night, or by the number of stars. Or more recently, they sort hotels by the customer reviews, for example, the ratings or the popularity rank. But the disadvantage of that is it largely ignores the multidimensional preferences of consumers. And what's more important, it ignores the location characteristics of hotels. So when we say location characteristics, for example, near downtown or near the beach, so these location-based characteristics, they influence the desirability of hotels, which will in turn influence the prices of those hotels. Well, however, very few empirical studies so far have focused on the location and hotel pricing. So what we want to do is we want to use hedonic regression models. This is a technique from econometric field. And we want to use this model to estimate the economic values of hotel characteristics. So hedonic regression model, basically it assumes that goods can be described by vectors of objectively measured characteristics. And consumers' valuation can be decomposed into implicit values of each characteristic. So basically a hotel product can be represented as a bundle of characteristics. So this model sounds perfect. Why don't we just directly use it? What is preventing us from using it right away? The challenge here is we don't even know what hotel characteristics we want to we can put into our model. And what's more, we don't know what kind of data are they. We don't know how to collect those data. So first, we want to identify what important hotel characteristics we want. We do this through an online anonymous survey by using Amazon Mechanical Turk, or MTurk. I will refer to this for short. So basically, we ask 100 people what characteristics you will consider the most important when you choose a hotel. And then we choose the ones that are most highly valued by customers. And we believe they will contribute to the aggregate price of hotels. And according to the resulting characteristics, we divide them into two categories. First, service-based hotel characteristics and location-based characteristics. For service-based, it contains hotel class, which refers to the number of stars, and the total number of hotel rooms, hotel internal amenities, which refers to, for example, free breakfast, wake-up call service, high-speed internet, and etc. And also, it contains a customer review count and popularity rank. The last two characteristics, we identify them in a slightly different way, which I will come back to this next slide. So after we know what service-based characteristics we want to collect those corresponding data. Our technique is validated on unique panel data consisting of 157,414 observations based on 9,463 different hotels located in the United States for the past 5 months. And the hotel prices and service-based hotel characteristics data, we crawl them from tripadvisor.com website. So during the crawling procedure, we noticed that the number of customer reviews and the popularity rank, they're changing over time. So we think, okay, this might be also interesting. So we added them into our model. So this is how we acquire the service-based hotel characteristics. And for location-based, it contains 7 in this category. Near the beach, near the lake or river, near public transportation, near downtown, near interstate highway, and hotel external amenities. This refers to, for example, near restaurant, near shops, near bars or market or any other attractions, and also safe neighborhood. And after we identify location-based characteristics, similarly, we want to collect the corresponding data. However, all the location-based characteristic information cannot be easily derived from the same way. For example, near the beach, we found that it's easy for using for analyzing image to derive this characteristic, because we noticed for beach image it usually provides a long straight sand strip together with large ocean area. So that provides us with very highly discriminating features, which is easy for machine learning algorithm to recognize. But for characteristic like near restaurant, it's almost impossible for discriminating these through image analysis. Therefore, our approach involves a combination of both machine learning and human annotators. Specifically, we collected the data through 4 different ways. First, Microsoft Virtual Earth SDK, which all of us are very familiar with. And second, image classification, and also MTurk online survey and data collection from online websites. For commercial characteristics, we compute them through local search queries using Virtual Earth SDK. So for example, we basically use the mapping service provided by Microsoft, and we search the total number of restaurants or shops or bars or markets around a specific hotel location, and we compute the total number of it, save it as the hotel external amenity. So that's how we collect the commercial characteristics. And for geographical characteristics, for example, beach or downtown, we notice that it's very hard for using the mapping service to acquire these characteristics by using local search query. We can't search beach or downtown, so we can't directly use the local search. Then we notice that, but we notice that their corresponding image actually they provide very rich textual information. As I just mentioned, we can see here is a long straight sand strip, and here is a big area of ocean. And also for downtown area, we can notice it has very dense intersection of the road and street. So we decided to use image classification method with gable feature extraction. So basically what we do is we retrieve the images using Virtual Earth tile system. And we get all these 256 times 256 images, and then we divide them into 49 overlapped regions, and we compute 48 features for each region. And after we conduct a feature selection, we tried different classification method on these 2 set of images, because although they have the discriminating features, but their feature type are different. So we found that actually we found the decision tree classification method works better on beach, and SVM classification method works better on downtown. So that's how we discriminate the geographical characteristics. But for some other geographical characteristics, for example, near public transportation, they are too hard even for image classification algorithms. Because, for example, if we want to know if this hotel is by subway station or not, usually the subway station, we can see a very little sign of subway train showed on this image. But it's very hard for machine learning algorithm to figure it out. But meanwhile, it's very easy for human eyes to recognize. So for this set of characteristics, we classify them using on-demand human annotation through MTurk survey. So basically, we ask people, do you think this image shows something related to public transportation or not? And for the last characteristics related to neighborhood safety, we acquire them from FBI online statistics. This includes city annual crime rate and also city population. So here's how we acquire location-based characteristics. And now we have identified what characteristics we want to put into our model. And also we have successfully collected the corresponding data. Remember, our goal is to locate the hotels with specific criteria and the best value for the money. So with all the data ready now, we can start our estimation. We use hedonic regression models to estimate the economic value for this hotel characteristic. We propose a linear function in this following form. So here, for the first summation part, are location-based variables. And the second summation are service-based variables. And C and S here are our control variables. C is a dummy variable for large city, and S is a dummy variable for holiday season. And the beta and delta here are parameters we want to estimate. And mu are random error terms. We use fixed effect vector decomposition estimation method at hotel level. This is a recent proposed estimation method from Econometrics field, which can capture the influence by time invariant variables in our panel data model. So after this estimation, we got two major results. First one is the economic value for each hotel characteristic. And we also get the residual value for each hotel. So what we can do from these two major results, for hotel characteristics value, here are our preliminary results. We notice here, there are two characteristics which will bring negative impact on hotel price. The first is highway. If it's near highway, the price would be lower. And also the average crime rate. If the crime rate is high, the hotel price will be lower. And also we notice here the popularity rank also have a negative sign, but it actually brings a positive impact on the hotel price, because usually the the smaller the rank index is, the more popular it is. Meanwhile, we also notice among all the location-based characteristics, beach has the largest positive impact on the price. So people really prefer a walkable beach, and a hotel by the beach can really make a difference in their price. Here are all the characteristics which will bring positive impacts on hotel price. Near beach, near downtown, near lake and river, near public transportation, and also hotel class, hotel external amenities, internal amenities, and the total number of rooms, customers' review count, and popularity rank. And here's what we can do what we can learn from the economic value of hotel characteristic. And remember, we also have another major result, which is the residual value of hotel. What we can learn from that, we propose define value for the money of each hotel equals to the residual value, which is the predicted price minus the real price. And then we rank all the hotels according to their value for the money. And then we got something interesting. Here is top 10 hotels we ranked with best value for the money in New York City during 2007 holiday season. And as we notice here, here are all the names of the hotel, and that is the corresponding number of stars of that hotel. We will say 3 star, 3 star, 4 star, 5 star, 4 star. And it pretty much covers a good variety of all kinds of hotels. And then after we get this list, we want to know how good is our ranking list. So we conduct user study to evaluate our ranking. So basically, first we generate 7 other different rankings by using the current techniques, including price high to low, and price low to high, and maximum review count, number of stars, number of internal amenities, total number of rooms, and popularity rank. We generate these 7 other different rankings, and we put them with our ranking together. And then we provide a short title for each ranking. And then we ask customers to select, to choose their favorite one. The result shows that regardless of the presenting order, more than half of the customers prefer our ranking. This sounds pretty good. And then we want to know how reliable is their evaluation, how robust is this result. So then we keep the title intact and swamp the underlying hotel ranking lists. So for example, we keep the title best value for the money, but we use the ranking list actually generated by hotel class. Then we realize that customers overwhelmingly vote for the ranking with the title best value for the money. So this, on one hand, it shows people really prefer hotels with best value for the money. But on the other hand, it also implies that their choices, their decision got largely influenced by the title. So because of that, we decided to conduct a pure blind test. We hide all the titles and conduct pairwise comparison with using our ranking list with each of the other competing alternatives. And then we are very happy to see that more than 80% customers prefer our ranking. So this would give us very, very good confidence that our ranking is better than current techniques according to our user study. And we ask the users their reason, and here's some voice from the people. They think our ranking provides a better diversity, including 30% of 5-star hotels, 40% of 4-star hotels, and another 30% of 3 stars and including below. And also those hotels are priced competitively. And our ranking result also provides a logical way to present information, which start out with lower level class hotels and generally increase to 5-star hotels. This will give them, this will help them to make a decision much easier. And here's the explanation from the users. And here is the further explanation from us. Based on the qualitative opinions of users, diversity is indeed an important factor that will improve the satisfaction of consumers. And our economic-based ranking approach introduces the diversity more naturally. And so here is what we got from the best value for the money. And what we want to mention here is we also notice something looks more interesting to us. We also rank the top 10 worst value for the money and for New York City hotels. And guess what? We notice the top 3 worst hotels, 4 stars, 5 stars, 4 stars, they're all from the luxury end. And compared to the top 3 hotels from the best value for the money list, they're most from the middle level 3-star hotels. And we think this is very interesting, and we to make sure this is the real case or not, we also tried some other big cities in the United States, for example, Washington, D.C. and Philadelphia on the east side, and LA on the west side, and also Miami and Austin, Dallas in the south. And their results shows the same trend. So we can't help asking this question. Are those luxury hotels there the worst? So this might be something very interesting to discuss later when we have more time. But we would really want to ask everybody here, what do you think? Do you agree that the luxury hotels, they contribute the most to the worst value for the money? And according to your own experience, maybe you have some different idea about this, or maybe you can explain this more reasonable. And finally, just for fun, we also rank the best value for the money for Greater Seattle area. And guess who is the best? Heisman Hotel, Kirkland. We believe this is the best one. But we really like it. So here's our conclusion. We empirically estimate the economic impact of hotel characteristics using econometrics modeling, user-generated content, and image classification. And by incorporating the economic value for hotel characteristics into a local ranking function, we can locate hotel with specific criteria and providing best value for the money. Here's our future work direction. First, we want to look into longer observed data set. And we also want to look into demand data aside from the price, and which can give us a more reliable analysis from economic point of view. And also, we want to conduct tax analysis on customers' review contents. Also, we are planning to conduct personalized ranking instead of just a general ranking. And we also think about using street-level images for better inferences. So, thank you.
Have time for So we had time for one long or two short questions.
The set of characteristics you described was this set derived somehow from users' opinions, or is this a set that you kind of made up in advance?
You mean the location-based characteristics?
Yeah, all those criteria that you evaluated. How did you come up with that list?
You mean how we identify those characteristics?
Yeah.
Yeah, we conduct through an online survey. A survey. It's provided by the technique we use is provided by Amazon Mechanical Turk. So basically, it's an online tool. We can distribute it small tasks and ask a big amount of people to finish the tasks, and we pay them a very small amount of compensation. Okay. So it's all through online.
I see, but did you ask those people to indicate which of the listed criteria are more important for them, or did you ask them what criteria they would consider when selecting a hotel?
It was open-ended, so if we can get a microphone to do.
We just asked the users what things you would consider important when choosing a hotel, and we left it open-ended. And then we had 100 users, the most frequently mentioned ones, above 3 out of the 100, we picked them as candidate features.
Other questions? Yeah, Vincent?
Yeah, close to the microphone, so just ask questions. And you mentioned about actually, done based on your experiment, that more than 80% of users are sort of satisfied with your ranking. Mm-hmm. And can you elaborate a bit more about how actually you did this verification? More than 80% of users sort of satisfied with your ranking.
You mean especially for the blind test, is it? The last one?
Go back to the slide.
Oh.
Okay.
Yeah, the blind test.
Yeah, so we hide their titles, and we just provide them with our ranking, the top 10 hotels, and also with one of the other competing alternatives from the 7 different ranking lists. So we ask people, which one do you think make more sense to you? Like you think is better.
Have those users sort of stay in those hotels before, or they have personally ranked those hotels by their experience?
Those person are random customers. Yeah.
So they actually have not been staying in those hotels. So just based on your criteria.
Some of them mentioned they stayed there before, and some of them haven't stayed, but they know something about that. So it's like all kinds of customers, not special kind.
So those customers were just looking at your those different parameters and sorry.
They were just looking at 2 lists of hotels, and they were saying which, if you were searching for hotels in New York City, which of the 2 lists you would prefer to see as a return of a hotel search on the travel website.
Yeah. Let's take one more question, John, on the back, and then we'll move on. Don't worry. No, nobody's running away. You have a chance. We can meet again tonight. There's more questions. Please.
You could argue that in an efficient hotel market that all the people who set the prices on hotels want to drive the residual value to 0 or negative even. And so I wonder if that, maybe the people who set the prices on hotels know more about the value of the hotel than the people that you ask. So I wonder if maybe they would be a better source of what criteria to use to measure the hotels by, since they're setting the prices.
Yeah, that's true. But usually hotel owners, they prefer to set hotel price much higher than their real value. That's what they actually usually do. They want to prove.
Realistic price. Who's going to pay it?
I think you'll have a chance to talk in a second, but I think for next year we'll invite a bunch of operation research people, and then we get an answer for that. Thank you. And the next speaker needs no introduction. The inventor of the quad tree himself, Hanan. And I can't wait to see the next talk. Thank you.
So we can talk later, except I'm on your talk. And it says ranking evaluation. So how do I get to mine? I'm not supposed to talk on this. I don't want to touch anything. Oh, no, I'm on the top here. Okay, I see.
Okay, there you go.
Okay, all right, sorry. Okay, oh, which one here? This one? Okay. This one? Here. All right, okay. All right. Okay, my talk is titled A New View on News, as myself, and really when my students, Michael Lieberman, Danielle Panozzo, Jagan Sankaranarayanan, and Benjamin Teitler. And Jagan and Mike are both here, and they're sitting right there, and we'll do a demo tomorrow as well. So let's get started. We're looking at news reading, and news articles often have a spatial focus, so the key question, at least to us, where are the current top stories, how do we find them, and also what's happening around the world. And we can give examples like in Asia, India-Pakistan border, I'd say my neighborhood. We don't want to restrict, enable you to go anywhere. Now, we developed a system that we call Newsstand, which stands for Spatial Textual Aggregation of News and Display. And what we do is we crawl the web for news articles. Currently, we're indexing 3,000 news sources. We aggregate news articles by topic based on content similarity. So our articles about the same events are grouped into clusters. Although we don't tell you in advance what the events are, the system discovers them on its own. Now, we rank the clusters based on importance, which is determined by the number of, let's say, articles in the cluster, number of unique newspapers in the cluster. For example, an event in Redmond, Washington is important if it's in multiple papers, especially if some papers are geographically far from Seattle. In other words, the scope or the distribution. And also, we look into the story's rate of propagation. Now, the idea is that important stories will be picked up by multiple papers within a short time period. If it takes a long time period, it's not that as important as in the short. Now, we also leverage work that we've done in a system called STEWARD, which is just a document retrieval system with geographic location. And what it does is it associates clusters with their geographic focus or foci. And what we do is we display each cluster at the positions of the geographic foci. Now, the motivation is really started with our work in spatial databases, where there's a you always have this distinction in queries between in spatial locational data, which is between a location-based query and a feature-based query. Location-based queries are the form, given a location, what is there? And we're talking about a lat-long specification. In terms of feature-based queries, it's really the same as spatial data mining. What you're saying is you're saying, given a feature, where is it? Now what we've done is we've extended the distinction to textually specified locations. So you'd say, find me all topics, articles that mention a given location or region. Alternatively, for the feature-based, you would say, find me all regions mentioned by articles about a certain topic. Now the topic is not necessarily known a priori, and the topics are ranked by importance, which could be defined by the number of articles that form them. And now we do one step further. We further extend the distinction to locations specified visually and by the direct manipulation actions of pan and zoom. So you see how we sort of run the gamut of the specification. Now our goal is really to change the way news is read. Now what we're doing is we're choosing a place of interest and we're finding topics, articles relevant to it. Now again, these topics and articles are determined by location and level of zoom. So if you're really zoomed in, you have a different focus. Now there's no predetermined boundaries on the sources of the articles. So some applications could be monitoring of hotspots. For example, investors, national security, disease monitoring. And what we're doing is really fundamentally changing the way news is read and presented. So one action is summarize what are the top stories happening, exploring what's happening in Darfur, or discovering patterns. How are the Olympics in China and Darfur related? You might not think they are, but if you look at some newspapers, you'll see there's a big relationship. Now, the ultimate goal is to make the map the medium for presenting information that has spatial relevance. Examples are news, search results, photos, videos, things of that nature. Now, let's look at existing news readers. Look at Microsoft Live. I'm sorry I'm a rude guest, but it's rather primitive, and the top stories are presented linearly. There's really at least little or no classification by topic. The Google News Reader classifies articles by topic, if you know, and also has a little feature called Local News Search. What it really does, it aggregates articles by zip code or city-state specification. For example, you could say, give me articles mentioning College Park, Maryland. It provides a limited number of articles, let's say 9 at the moment, and it seems to be based on the host of the articles. In fact, a lot of people attribute geographic location by the little tagline. You look at the AP stories, they say Washington, D.C. or something like that. Now, so we say the LA Times provides local articles for Los Angeles. If you look at Los Angeles, not a bad idea. Look at the LA Times. Okay? It seems to use Google search with location names as search keys. For example, when we look for articles for zip code 20742, where the University of Maryland is, they're really those mentioning College Park, Maryland, or University of Maryland. It doesn't seem to have a notion of story importance in the grand scheme. And if you look at international versions, it really means international news sources. All right, so as I said, it's really closely related to STEWARD, which is stands for Spatial Textual Extraction on the Web, Aiding Retrieval of Documents. A mouthful, but you got to have a name that means something, and people like to, they'll never remember what it stands for, but STEWARD. Actually, STEWARD is a great name. You know why? Because STEWARD acts like a guardian. And what we did this is for government documents and for the Housing and Urban Development Agency, and they viewed it, hey, this is STEWARD is a caretaker. So it's not a bad name, okay? And again, these acronyms, what you do. All right, so what is a document search engine where you have an example spatial textual query would be, let's say you're looking for a rock concert. The location, let's say, near Bellevue, Washington. What we want is resulting documents that are relevant to both the keyword and location. So for keywords, pretty easy, mention of rock concert, but you want a spatial focus near Bellevue, Washington. So why do we want to use it? Well, try it on a conventional search engine. What we want is a preference for documents containing both Rock Concert and Bellevue. Now, the question is it the intended Bellevue? What about rock concerts in Redmond or Kirkland? You'd like to get them as well. So the deeper issues are you want to take spatial synonyms into account. Most search engines don't understand the various forms of specifying geographic content. So we really want more than just postal addresses. And the results on most of the search engines are really based on other measures, link structure, things like this. In other words, if people link to you, they'll find you. If nobody links to you, you could have the world's greatest stuff, but no one will find you. So it's more of a popularity contest and what I call the democratization of search. And why do I call it democratization of search? Because if you give someone crap and they don't like, everybody gets the same crap. In other words, if you search for something, you don't find it, the other people also don't find it. So how can they complain? Okay, do you see the distinction that I'm making? And, you know, maybe I said too much here, but that's what link structure does for you. So we're saying that STEWARD is not really Google local in a sense where it uses, you know, really geocodes postal addresses and the points on the map. And this is not so hard because address strings are generally well formatted and most results can be drawn, let's say, from online yellow pages, things like that. What we're really doing with STEWARD is really working on unstructured text documents, where the document is really a bag of words, and the goal is more than searching for addresses in documents, which is really easier. So the goals, as I said before, is really to identify all geographic locations mentioned in a document, find the geographic focus of the document, which means what is it really about, but just in a geographic sense, okay? And retrieve documents by spatial textual proximity. So, having said that, how does the newsstand, different from STEWARD? Well, newsstand focuses on finding clusters of articles on a single topic and associated them with the geographic locations they're about, and to a lesser extent that they mention. Okay? Now, STEWARD focuses on determining the geographic focus or foci of single documents. See, now we're working with multiple documents. The beauty of working with multiple documents is that the noise doesn't stand out. In other words, if I've got like 100 articles, well, if one article mentioned Redmond and no other does, well, Redmond is not going to be the focus. So what happens is the clustering somehow helps you in finding the geographic things because the clustering is based on a lot of terms. It's like maybe, huge feature vector, we use TF-IDF business. And so the locations play a small role, but the ones that are the same play a big role, okay? So that enables us to actually find the foci by having a lot of documents. So what I say here is that newsstand can choose to ignore some locations as being irrelevant to the central topic of the article. And the common topic of the cluster is used to improve the geographic foci determination process. In STEWARD, the user selects the keywords that determine the documents. Could be news articles, but we also do it for PubMed, ProMed, and things like that as well. Now, in Newsstand, the topics are more general than keywords and are determined by the clustering process, okay? And that's independent of the user. And also, the Newsstand can use the functionality of STEWARD to enhance the process of reading particular articles in the cluster. For example, you could search the cluster for keywords, browse the geographical foci of the elements of the clusters as well. So, mapping the news. Well, we ignore the source geography, the newspaper location. When I say ignore, not completely, because we sometimes use it for hints in certain cases. We use the geotagger to identify references to locations. Here's an interesting thing. One of the things we're able to do is to take advantage of zooming in. Zooming in is a very important feature, but it's sort of a problem. What it means is that the cluster populations will be smaller as fewer articles refer to the viewing window. If I give you the whole world, of course you can cluster the most important stories because there's millions and millions of stories. They're not all, some will be more important than others. So it's a self-selection. In other words, self-selection gets rid of the bad articles. Not bad, but the less important ones. But as you're zooming in, you can go into Bangalore, into streets in Bangalore. Well, they're not going to be a lot of stories, but the point is those articles are not going to be that specific. They'll be more prone to errors. So what we're saying is that location plays a larger role in the clustering algorithm, but geotagging errors are less likely to be filtered out when you're zooming in. Now, we also have something called cluster rank versus cluster spread. When we show the stories, we don't want to have empty areas on the map with no articles. So this implies less important articles are displayed with some regions than others, and some important articles are obviously not displayed unless you zoom in. So as you zoom in and pan, you want to make sure that once an article is displayed, it persists until its location is no longer in the viewing window. Otherwise, people get disoriented. Now, zoom in and pan are really expensive as much redrawing. And what you'd really like to do, and it'll come up with us, is use an inset overview window to control the zoom and pan with little symbolic information that needs to be redrawn. So, what are some general geotagging issues? For example, you've got to identify the geographical references in the text. Does Jefferson refer to a person or to a geographic location? How about disambiguating geographic reference? Does London mean London, UK or London, Ontario? There's 2570 different Londons in our corpus. Also, you want to determine the spatial focus of a document. Is Singapore relevant to a news article about Hurricane Katrina? Not so if the article appeared in the Singapore Straits Times. So you got to worry about these things. Now, some news-specific geotagging issues. The name of the news source. As I said before, that's like you identify geographic focus for a particular news source in terms of the containers of the articles in the source, and you use this to resolve geotagging ambiguities. Okay, I don't know if you understood what I'm saying here. What I'm saying is that if you have a newspaper, one of the things we do is we cluster the newspaper themselves. In other words, what you'd like to know about the newspaper, is it a local throwaway? Is it a national newspaper like the New York Times? If it is, then the stories will have much bigger scope. Whereas if the newspaper is, like the Kirkland Daily Herald, I don't know, whatever it is, the stories are going to be about Kirkland. Therefore, when you see stories in that particular venue, and you see a name like London, it'll most likely be a London that's local instead of something else, because this is a very hard problem, what we're looking at. I mean, to get it right or to get things done. Now, so another thing is you could perform some preliminary clustering by focusing on the headline. The headline often says a lot, okay? It says little, but it says a lot too. I mean, in the little that it says, it's conveying a lot to you. I mean, you have to understand there's sort of a play on words on this, but there is some importance there. Now, the other one is you have a multiple versus a single interpretation as a geographic location. Multiple means that if I have a lot of interpretations for a name, it probably means it's probably a geographic location. Okay, whereas if you just have a single interpretation, it may very well be an error. So there you could verify by checking the population, the presence of containers. In other words, if I see someone like Manchester, not Manchester, but a name a name that can also be used as a name of like Obama, for example. There's a place called Obama. If you see Obama, I'm going to say because Obama appears in the genus, I'm going to place every place Obama in. Where was Obama? Japan. Okay, there's an Obama in Japan. Well, we don't want to report Obama in Japan. We look pretty silly if we do that. So you get so these are these clues right here. And we're looking for presence of containers. What's a container? It's like a hierarchy. And people have used containers in this spatial textual world, but what they do is they use containers for a lowest common denominator. In other words, saying, well, I got a story about Kirkland, Redmond, and other places, therefore it's Seattle, because what they have in common, they're in Seattle. But we're looking at containers not to give you an identification, but really to sort out problem things. And also the presence of proximate locations. An example like this, if I have London, if I have Toronto in the document, a few other places, then it's going to be it's much more evidence for London, Ontario than London, England. Okay, and the point is, so we don't, the natural way of doing is to look at probability and say, well, if you got London, it's got to be London, England, because that's the biggest population, the biggest thing. Therefore, it's got to be that. And what we're saying, no, you can't make such decisions. We're trying to get it right, or at least use more evidence. So there's a lot of learning aspects here as well. Okay, so the architecture of newsstand. You have these RSS news feeds, and you can see right here, sort of the structure, the document acquisition. There's the geotagger. I mentioned that before. You have feature vector extraction, feature record. So if we go here, so this breaks up the document into entities. The feature record assignment associates each entity with a list of potential geographic locations, and we use a gazetteer. There's another problem. Find a decent gazetteer. We've been through a whole bunch, and none of them really have all the information you need. Somebody could really compile, it's really worth something. Like a service, and to give the information. It's just not there, okay? Disambiguation via semantic analysis. This is how we determine the correct geographic reference for an entity. Then we have the geographic focus determination. It's like saying, pick the geographic references most relevant to the document's content. Okay, so here, I mentioned the news cluster detections use DF-IDF, type work. I'm not going to repeat that here, so we don't have much time. Feature vector extraction methods. We said before, is Austin a location or a person? They have these problems here. We try to use natural language-based techniques. So we want to find noun phrases or potential locations. For example, we avoid names that are followed by a verb or an adverb. So sort of rule-based type thing. Of course, none of this stuff is perfect. We use a corpus as well. Natural language techniques, we use corpus. In other words, as part of speech tagging, named entity tagging, as well as rule-based approaches. And then this is the feature record assignment where we actually interpret things. And how much time do I have, Gur? Okay, so I still have, all right, okay, all right. I just don't want to be stopped before all right. Okay, so I go back here. So the feature record, assignment, well, I want to give you your money's worth, the price is right, it's free. Anyway, so we search the gazetteer, and you have a corpus of geographical locations. So this is, for example, genus, you got 2.06 million locations, and it also contains hierarchy information, as well as alternate names. Still, it's not enough there. For each word and phrase, we obtain the list of all possible geographic locations could be, and then we try to associate the keyword with at most one location. Okay. Semantic analysis, we mentioned before. How do you know which London it is? So I mentioned that if you got Toronto in there, it might be more likely to be London, Ontario. And we try to make use of this idea. We have something called a disambiguation algorithm, which we call pair strengths, where we look at pairs. So you might have, if you look at London here, it could be in the UK and Canada. These are the options. And so we have London, UK, London, Canada. And we look at all pairs of entity location combinations. You have London, UK, London, Canada. These are the interpretations. And suppose we have Hamilton in there. Well, there's a Hamilton, Canada, and a Hamilton, Bermuda. So we sort the pairs in decreasing pair strength, like features like how far apart they are or things like that, to enable us to to find the strongest pair. And of course, we ignore assignments with weaker ones. Okay, so where did we go here? I wanted to go next. What happened? Oh, I used the wrong. Okay, where are we? Okay. I got lost. All right. Anyway, so here, if you use the, because I got 1 and 1 here. You see here, if we say distance between them, so the pair London, UK, Hamilton, Canada is weak, whereas London, Canada, Hamilton, Canada is strong. So for the, to give you that interpretation. So we're trying to show you how we would interpret where London was. I know it's a lot of stuff here. we talked about geographic focus. We'd like to have, which one is it? And we look at frequency in the document, but not necessarily spatial proximity to other entities. Container-based method. Every entity votes for a set of container objects. If they're all there, it gives greater evidence. We also use clustering-based methods like agglomerative methods. And we use really a combination of all of these. Okay, now the user interface, we use a mapping API provided by Virtual Earth. Some improvements that I mentioned to Gur already today. I'd like to have the ability to recursively invoke the Virtual Earth. Why? Because there are certain tasks you want to do again and again, and you don't want to open. In other words, we don't want to open a new window. We want to have like an inset window, and the fact where your mouse is, it tells you where the action is. A very powerful user device used in maps. Insets. The whole notion of insets in cartography is really that. Okay. So, and some application scenarios are the spatial textual search engine for the hidden web, which I mentioned before. And also we've done it for infectious disease monitoring. We scan newspaper articles, ProMed alerts, and we identify infectious disease mentions using a disease ontology which we've developed. So now, instead of just having a geographic focus, we also have an ontology focus for the document. You see that the same techniques that we use to do a geographic, you can do other topics. Of course, you're not getting all knowledge, but you can devise an engine or a device for a particular subject, and you can use that knowledge that you have about the subject. So that's, so the idea is that, let's say, to map disease alerts in real time. Okay, so acknowledgement, I'm going to do the demo. And I want to acknowledge our support from Microsoft Research and Virtual Earth. HUD, Department of Housing and Urban Development, in the name of John Sperling. Some of you met him before. Has been our collaborator on this, and he and I sort of hatched all this stuff at a meeting a few years ago, and we work very closely together. The Digital Government Program at the National Science Foundation and Larry Brandt and the University of Maryland, who also supported us in doing this. And I say supported us, it means they actually gave us money. Not money, but in other words, they didn't just say, okay, you can do it. So I should acknowledge it. All right, so now, how do I get to the bottom here? Remember? Huh? Oh, escape. All right. Right. Oh, but I'm not supposed to escape. All right. Okay, so I'll give you a little demo here. Okay, so here, I should mention, these are, news articles. We froze it a couple of days ago so that, we don't have this problem that suddenly something doesn't work here. But this actually works in real time and clusters things as well. So here's a map. And you can see that we have the different colors here and sizes, okay? The color has to do with freshness, okay? The light green is older, the dark green is newer, and the size of the box has to do with importance, okay? So here is an interesting thing. If I go here, you see, let me click on this story here. You see they light up, okay? And what is this story is about, arms to Zimbabwe. And if you look here with the tents, it shows you the locations where this ship has been going, okay? There's a ship of arms for Zimbabwe that no one wants to take, okay? And here are the stories, okay? So if you look here, this Angola, Chinese ship carries arms cargo to Mugabe. And you see Namibia. It's sort of neat to look at it. South Africa, didn't go there either. Here, what do we have? Another South Africa. Here we have, Zimbabwe. And if we go here, come on, all right. Okay, you got Mozambique, and here you got China, okay? So you can sort of follow what's going on, okay? Let's go here for a minute. Okay, hey, this is Jimmy Carter's trip. You can follow Jimmy Carter trying to be a peacemaker. And if you don't like it, let's see, how do I, oh, this is supposed to, okay. Why isn't the mouse working? Is this, it's supposed to, damn this, huh? Huh? Oh, okay. It's suddenly slow. All right. Okay, I'm sorry. Anyway, so you can see I zoomed in here, and you can see that these are where Jimmy Carter, okay, Egypt, Gaza, where else? Here is, Syria, and here we have Damascus, and these are different stories here, but you can see the articles, you can sort of follow him around, and you see the zoom here, what else can I show you? Okay, all right, so let me zoom in on India here. We didn't have many stories because, remember what I said before, it's partitioned the world so everybody has approximately the same stories, but now as I zoom in here, okay, you see I'm getting closer, and if I zoom again, okay, what's happened? All right, let's see. This mouse doesn't react, or, huh? Oh, I did. That's why I wanted to use. It's supposed to. All right, but this mouse is not reacting, huh? Huh? I did. You see, it's, huh? Which one? Oh, okay. All right. Let's try this. If I can find it. All right. This zoom in should be, no, zoom in. Okay. All right. For some reason, it's, Virtual Earth has the controls here as well, and it should work with the mouse, but this mouse is not responding to double click. But you see what happened here in India? We got many more stories about it, okay, as we zoom in. And of course, they may not be, but you see here more. And you see, why are these here? Because they're plotted, they're about India, so they're plotted in the center of India. But here we have stories that are more relevant to these locations. See, Bangalore, oh, what do you know, Kantar? I didn't do this on purpose. Okay, but you can see here we're getting Bangalore. But you see how we're focusing in, and you see as you're, zooming in, let's see, let's go on Sri Lanka. And we're getting stories on Sri Lanka, but in the grand scheme of things, you didn't get anything about it. Okay, so now let's zoom out for a minute. Okay, so we'll get back, well, it takes us, all right, to, because it's still, when it's zooming out, we're working in Maryland here, okay? So, all right, so here, let's look at something else that's in, let's zoom in on here. Oh, okay, this should be the zoom in. Okay. And we want to get into Chicago here, just a minute. All right, where's Chicago? Oh, it's, can you see? Yeah, I think this is the one. Is this the, yeah, earthquake. Okay, so, all right, so now, all right, so here, if I click here, I get the story. But if I go here, I get the various stories on Chicago. Okay, so here, what you can see is you get all the stories. If I hit title, it'll sort the stories about, about that particular topic, which is the earthquake, alphabetically. I can also sort by the stories here. These are domain things. We're going to convert them to the real things if we can. This is by date. It gives you the freshness. You can do increasing, decreasing. Now here, let's go back by title. Well, let me just go back to where we... Was this the first? No. I'm trying to think. Is this... where's the close here? Let me just go back here again, because I got confused. Okay, let me just show you this. Okay, so let's go to the story here and see it in STEWARD, okay? And you can see a little power here as well. Now, I can make this, fill the screen here. Where is the... Anybody see? Oh, here, right? That's it. So let me maximize. Okay, so let me zoom in. We have this uses Google. It's not Google. We're just displaying with the Google API here. Where's plus? Okay, so let's go in there. Okay, so here we're really, STEWARD would actually find lots of articles, but here we're just looking at applying STEWARD to this article. And if I hit focus here, okay, look what happened. Now, I'm looking at terrain, but I can just look at map. And what you're seeing here is different markers of the different geographic locations mentioned in that article. And the colors have to do with the confidence that we have in our classification. So what you see right here is what Illinois. Okay, so if you go here, you can get, it just shows you the textual extracts where you find Illinois here. Number 3, number 6. Well, if I go here, I get other references. Well, Des Moines was number 2 in importance here. So you see, now I can see all the Des Moines mentions. They're just twice. Okay. If I click here, I get the other one. If I go here, I can get the next one with Cincinnati. All right. Now, okay, one of the things you see here, suppose I made a mistake, okay, and it was a different Cincinnati. Then what happens is I get options here where, I guess Cincinnati was only one. Let's see. Do we have other ones? All right, Mount Carmel. Okay, so let's see. Suppose this is an error. And what do we say here? Not loc. What should I do? Huh? Which one? I'm trying to. Oh, there. Okay, do you see all the Mount Carmels here? Okay. These are all the options we can do to correct it. And once we do that, it's corrected. So if it was an error, it won't make that mistake again. Okay? So, and the other thing that's supposed to be here is, you know, let's see, where's the highlighted copy? It's in there? Huh? It was supposed to be. Where is it? Huh? All right, okay. All right, okay, let me, where's the other one? Okay, let's see, so, okay, let's try another story. Oh, that was a mistake. You see, when you, just a minute. All right, so we'll see it in STEWARD. Do we have one that? Okay, so this should be a story here. And let's, huh? It's the same one.
Yeah, no, because the system was not caching these stories for a short period of time. So
for a few minutes before. So that's the, so what do I do here? Nothing?
You can try another cluster.
Oh, well, all right, so, huh? Okay. How do I get to another cluster here? All right, okay, by closing. What you're doing, go to another story, you're saying. That's what you're really saying. So let's go with our friends in Africa. You think they'll be clustered? Okay. Let's go to Robert Mugabe, okay? His ship has been going everywhere, right? So let's go here. And hopefully one of these stories will have it. Okay? And that's sort of a neat thing to show you. Oh, that's the. I should have gone to STEWARD. Anyway, this is hot off the press. Okay, if you want to. All right, so let's try this, and hopefully this one was. It's not.
Need a more recent story. Try more recent.
Well, I mean, when you say more recent. Okay, so you're saying a more recent story, meaning a really dark one. No, a recent is light is no. All right, anyway, I think what it's supposed to do here is show you a PDF with everything in there. Okay, and we'll just try one more. And again, we had this breakdown before. Okay, and tomorrow we'll have the highlighted copies. Oh, here it is. Here it is. It's here. Okay. Okay, this one. Okay, here it is. Okay. That's what I wanted to show you. You see? the locations. So you say Canada, get the next, it'll get the next one, and it should get, all of them highlighted in the things. You can step through the document and see all of the locations. And that's the idea. Okay, and I'm sorry to run a minute over. Any questions? Yeah. Pushing?
Thank you for a good talk. Thank you for the talk. It's very interesting. The first question is, you mentioned you do the clustering, then you do the geo-tagging. I just not very follow. Why are you doing the clustering first, then you do the tagging? Because they have many methods. You can do the geo-tagging, then like Makata. I'm just curious how accurate of this the method you're using the clustering first, then you do the geo-tagging.
No, because there are two systems going on here, okay? I explained to you the newsstand is a clusterer, okay? And what you're doing with the clustering is you're trying to identify what, what are the common...
That part I can understand, because you using the grouper or whatever, they're doing the similar thing, right? They group the newspaper based on the subject. Then you find what's
yeah, but afterwards
centroid.
You try to find what are whether geographic, those are the geographic locations that are there, okay? So what you're saying is, why don't I geotag first?
Right.
Well, that's sort of an optimization that you could do.
Okay. Another question is, if we have the real time the updates for the newspaper, how do you update your cluster and?
Okay. First of all, real time in a sense they're coming in. I can't cluster that fast right now. Okay. The clustering takes time. Okay. It's not, but I say it doesn't take days. Okay. And the clustering that we just got running today, a clustering algorithm that goes much faster than the one we had before, which was sort of brute force type things. Is that fair to say? Yeah. But so the point I wanted to make is about the RSS feeds and all that. The RSS feeds don't get you that much information because most of the news is not there. If you want to get all the news, then you're throttled. Okay, so you can't really get at it because nobody will let you go to their website very much. Okay, so we have what we can get, but we have a lot of sources, but doesn't mean we can get them day and night, of course, but there's no reason why you can't do that with our work, okay? I'm just saying we didn't necessarily have it. So our clustering, again, that you're getting here, it takes hours to do right now, but the new ones we have are much faster, and one of the things we're working on is developing clustering algorithms that are super fast, and one of the things we're working on is using GPUs and other parallel. We're working some on cloud computing and things like that as well. We've got a lot of things in the fire, irons in the fire, but we're only 4 people or 5 people. There's a limit, and that's it. So yes, yeah.
Yeah. You did mention, I more than agree that for news search and you pay less attention to the address within the documentation. But in one of your criteria, you did mention that you actually pay less attention to the source of news, which I think is a little bit debatable because looking at the news is the most important news for the local is actually how influence or impact to the local. For example, Microsoft News. A lot of people would read the news related to Microsoft in the greater Seattle area, but in that news, probably there's no location about Microsoft or even those locations
but
not there.
What we're saying to you is that we're looking at news from a geographic. We're trying to show you news from a geographic context. What you're saying to me is, hey, Microsoft is in Redmond, therefore you should infer that the article is about Redmond. Sure, but I can't do that. Okay, I'm just saying that. Okay, but that's not what we're looking. We're trying. Our goal has been really to try to identify geographic locations. We use this as a vehicle to do that, and we found very interesting applications you can do with it. But the fact that we can't do everything shouldn't be. We make a ton of mistakes. I could have showed you a zillion errors, but my students asked me not to be deprecating and not to say that it doesn't work perfectly. But that's life. I mean, nothing is perfect. And I can tell you, we have a problem with Santa Catarina. Have you heard of Santa Catarina? There's a Brazilian priest who flew off with a bunch of balloons, okay? And no one's found him, okay? He's even got a chair on his balloon, okay? And there's stories everywhere about him. And in our system, the gazetteer doesn't have Santa Catarina in it, so it puts Santa Catarina in Mexico. And I was furious because I heard of Santa Catarina and it wasn't right. And I said, how can we miss it when we found Brazil, but we didn't find Santa Catarina? And I even told my student, I said, Santa Catarina is a really famous place, but no one heard of it. So I'll tell you, where Moses spoke to God is in Santa Catarina. It's called Sinai, Har Sinai. That's in Santa Catarina, but you didn't know that. But a lot of people do, okay? But they wouldn't have thought Santa Catarina in Mexico. That's what I expected, to get it in Egypt, but not in Mexico. All right, you see, that's funny, but not so funny. All right. Yeah.
All right, so it's a very nice talk, Hanan, and very important topic. But one other challenge which sort of you alluded to in the last example, many articles refer to multiple locations.
Right, we do.
So, you know, the first location often is where the reporter was based. So many stories on Afghanistan, if you read NYT, the first thing you will see is New Delhi.
Yep.
And then in the article, it will kind of talk about the current location of event. Then it will give you the history, what else happened nearby. So if an article has multiple locations, how do you choose the one where it should be indexed?
What I said was that, first of all, we try to avoid, not avoid, but we don't take where, you know, just because the article was filed in New Delhi, it's not about New Delhi. And what we're trying to do is find evidence by other locations in the place that would give you that. And where you say, how do we know what the main location is? Well, if you look at STEWARD, you don't know. But if you look at the clustering algorithm, what happens is that the topic of Afghanistan, Taliban, and all these things, they dominate. So each one may have other locations, but the common theme will be Afghanistan or something like that. So Afghanistan will stand out over everything else, and you avoid this thing about multiple. However, if you're just looking at one document, which some of our documents, news stories are short. The documents in the HUD repository are maybe 500 pages, and we're going through 500 pages. There's no way we can give you one location, and we get screwed up left and right. There's a bibliography. You got all the, you know, the thing, you know, where the, you know, people are. You have mayor of El Chinito, the El Chinito City Council. Does that mean that it's a place? You know, there's lots of, you know, this stuff is, you know. So you're sort of asking me about it. You're picking on the reporter. Yes, and that's the point I wanted to make. Most of the places that look for locations, they really look at, hey, AP says New Delhi or, you know, something like that, and say, well, it's about New Delhi because usually they're right like that. But I gave you the example about the Singapore Straits Times, and I saw that in a real system that flagged Hurricane Katrina stories in Singapore, you know, in Singapore. That's why I said it.
Okay. So, thank you.
All right, and my apologies.
And I absolutely encourage you to look at the demo tomorrow, and we'll have a chance to do it. No, it's great. Next talk is, you know, some people here complained that you know, big corporate America is destroying research by solving all your problems. Well, actually, the reverse, right? Like to you know, some people here are working really, really hard to make sure that you have this wonderful data set that you can then build upon. Oh, anyway, so Wolfgang runs, you know, our left brain, or right, I guess it's a right brain, in a way. He's this big coordinator force in the sky that tasks airplanes and cars and satellites, and, you know, spends a lot of money too. So he's going to tell us a little bit about what we're doing in the virtual Earth domain, specifically in 3D. And when you look at this, first, this is a very impressive piece of work, and I don't say it because I work on it. He is. I think the work he's doing in JSON 2 technology is very, very interesting. Conrad, of course. But also look at this from the lens of what can we do with this data set. Some of these problems have been solved when this is now available for us. What else can we do? So, Wolfgang, please.
Do I need to introduce myself? Because I missed the morning session. So, by the way, I'm feeling bad now because it looks like I'm the only thing between you and the great dinner. And so I promise I keep it as short as I can. How does that work? And you promised me not to fall asleep. So let's have a deal here. So actually, Gore said it, I'm managing the imagery data acquisition program for Virtual Earth, and as such, I'm dealing a lot with reality, with business reality, with facts, with weather, with climate, with political issues and all that. So my talk is not going to be very scientific. It's supposed to be provocative to some degree, nonlinear thinking, right? So I titled it the Geospatial Data Challenge for the 3D Web, and I need to explain about every single word in that title. Let me start out with what is 3D Web. And there's this famous guy here that made this statement at his 50th birthday, almost 2.5 years ago in Oxford, in a speech, when he said, "You will be walking around in downtown London, UK for that." So is that clear now? London, UK. And be able to see the shops, the stores, see what the traffic is like, walk in the shop, navigate the merchandise, not in a flat 2D environment like today, but actually in a virtual reality walk through 3D environment. And so that's the grand vision. And if you look at what Virtual Earth and Virtual Earth 3D is doing, we're working towards that goal in the hopefully not so distant future. But there's a lot of things that are needed to get there. Those are, for one thing, we need to have an actual geodatabase, a 3D representation of that real world, of those alleyways in downtown London and the shops and the stores there and potentially the interior one day. There's a whole lot of questions about the compute infrastructure, the servers, the user interface, and not least of all that, the business model that is, I would say, still developing and not at all clear at this point. The 3D databases, that's the stuff that I'm dealing with. So at an absolute minimum, what we need in there is the terrain and its textures for all the land masses on the planet. Plants, textures, man-made objects, buildings, bridges, everything. And we could add in moving things like cars and ships and airplanes, but at a minimum, we need metadata to describe all those things, where they are and how they correlate with each other and interrelate. Are we there yet? No. But we're making progress. So I think we demonstrated the capabilities and with the Virtual Earth 3D. We're now going into what we call the version 2, where we added a lot of realism, more content, more detail. I'm not going to go into any of that because I don't want to steal the thunder for Jason. Steve Stansel is coming, giving a presentation. So I just touch on the surface on that. And I drew a red line here. I would say this is about where we are today. Next things will be, well, there needs to be more functionality. Now, that's a very ambiguous statement. Let's put it that way. Today, we're mostly looking at the things, the maps, the 3D world, and the functionality that we see in applications mostly comes from overlaying it with other data sources. The mashup is the typical scenario. The other thing we haven't done yet is really scaling it globally. Yes, we're having some 250 3D cities online today, but if you look at the percentage of the population centers in the world, that's not a whole lot. There's a very small fraction of it. There's a good 5,000 really big cities in the world that we would need to cover one day and keep up to date. So that real big scale global approach hasn't happened yet. So I drew a red line for two reasons. Yes, that's where we are, but it's kind of a natural barrier. There need a few things to happen now before we can go further. We need for this to scale really on a global scale, we need a lot more automation. We're proud of what we can do today, but it's fairly limited to creating the initial product. What's not taken care of very well are two other things. Automated QA, QC, quality assurance, quality control. Automation is great if we now have lots of computers creating millions of buildings and we don't need an army of clickety-click people somewhere in an offshore factory working along. However, the thing falls apart if now for quality control we still need people to look at every one of those millions of buildings to make sure, yes, it's a good one. So there needs to be a lot more technology developed or implemented that allows us to do things like automated QC and automated change detection, figuring out where to update, when to update, why we want to update at all. So number 2 and number 3 of that list is still a big challenge. So that's kind of, why do I say that? Because there's a lot of smart people here. You all present a paper here and you're kind of done now with that and you're wondering, what do I do next? Rephrase it and try to give it somewhere else? Or maybe here's a new topic to work on. So that's my main motivation for talking today. So this colorful thing here is, before I talk further, I want to go back to the basics. What's the requirements? What's the reasons why we're doing all those things? What are the implications for algorithms we choose, methods we implement? I'm starting at the back end. So if we say we want to create geodata to support web-based applications, those applications in a very basic sense could be characterized initially at least as view and tour, explore. So what is that I'm looking at? And analyze. So the analytical functions get more complicated. So get me all the buildings with 13 stories and higher in that area because I'm looking to buy some real estate. I'm a big investment firm. So number 1 and 2 is what we can do today very easily with all the tools we have at our disposal. But number 2 and 3, they get a little hard because for that we would need to better understand the semantics, the content. What is it we're actually looking at? Now, all of those models we need are supposed to go into web-based applications. And with that come a lot of implicit requirements. And those are just a few ones here. But a small data size footprint to enable reasonable download speed and performance in a networked environment is a basic requirement. Simple structure means simple geometry, again, fast rendering on not so fast devices, making it available on mobile phones. You think of the web not just as the big desktop, but the beefy graphics engine and all that stuff. Now, with web-based, it comes the other thing. That it's totally open. It's the whole world. So you have a lot of non-PhD users who want to have things that they understand. For example, when we looked at these 360 panoramas earlier today, they look impressive for people like us who deal with that every day. But looking at one flat picture that shows back and front at the same time is very confusing to most users. The international aspect is very important for a couple of reasons. What we find okay might not be deemed okay in other places and vice versa. Remember last year was that, Franz, when there was still the old office in Microsoft Excel Graz, there's this elementary school kind of behind, and in that road, the street that goes over there is one of those big poster advertising things. And there was a poster on there it was advertisement, I think for socks or something like that, with a very naked man on there. He had black socks on, and that was it. And I was in front of an elementary school. That's deemed totally normal in some places of the world, would totally not fly in this country. So what I'm saying is what's what's acceptable in one cultural setting, in one environment, in one legal system is not entirely acceptable in other places. Privacy, security. We had heard some talk about the street level images showing pictures of faces and cars. People going into, what was it, porn shops and all the things that Google got famous for when they first released the Street View project a few months ago. We need to be careful when we create those databases that we take into account all these privacy and security aspects as well. So any grand system to drive through a street and create great 3D models and such that doesn't also have functionality to censor, to mask out faces or registration numbers for cars and so forth, is not going to work in our environment. We need those functions from the get-go. Gaurav, how much time do we have, given that I started late? It's okay. So geodata, it's not just 3D models. It's imagery, it's raster, it's vectors. It can be text, it can be multimedia, as long as it's georeferenced and put in a geospatial location. I just wanted to put that on for clarification. So how do we go about creating all these things? Well, the simplest thing would be there's a warehouse of data that's already there. We just need to geocode it, put it in the right location on the world. Actually, that's what we very early on started out with in Virtual Earth 3D. We grabbed the landmarks from the flight simulator and put them in the right place, and off we went. Hey, here's our 3D world. Aggregate UGC, user-generated content. That's a funny one. So our dear friends at that company, not to be named, went that route with the 3D content generation. There's the SketchUp tool. There's thousands, maybe tens of thousands or more of people contributing content. Now, that creates a lot of issues because it doesn't give us control over completeness, quality. We might get 10 people doing the same landmark and no one doing the 10 houses around that one landmark. And the alternative is we create it from scratch from other sources. But then there's a lot of issues about which sensors do we use and which sources do we use? How do we acquire those? From the air, from the ground, from space? Do we do it ourselves? Do we license it? Do we outsource it? As simple as it seems, when you start digging into those details, it can get very quickly very hairy. How much realism, fidelity do we want to have to meet all the requirements for our applications? And how do we actually eventually scale that to the level that this worldwide audience and the World Wide Web would expect us to cover with reasonable databases? And of course, all that, while there might be good solutions for this and that, we just need to buy this $10 million sensor and fly it on a spacecraft and all that stuff. By the time you build a 30 satellite constellation, this is totally not financeable. Is that the right word? So even Bill Gates will not pay for it, put it that way. Yep. So let's look at a couple of problems we have, right? So assume we build some content and we have users attribute it or add to it, generate their own version of that landmark. Us later maybe updating the same city or place from other sources. We immediately get into a lot of issues with how do we combine different data showing the same thing, different objects that are coming at different times from different sources with different quality criteria and so forth. It automatically, again, without having an army of people looking at that stuff. So what we need is means to compare objects in the database by by using criteria like correctness, realism, how old it is, what's the level of detail, and so forth. But any of these, if you want to implement it in software, we quickly understand that the software needs to better understand what it is looking at. So it's no longer good to have just points and vertices and faces and textures on it. We need to know this is a bridge, this is a building, this is a residential building, this is a parking structure, this is a wooden bridge, and so forth. It is vitally important to introduce some semantics, some image understanding, model understanding of the world that we are creating here, so that these algorithms can actually work. More realism. So I'm not talking about more, I mean, if you look at the newest computer games or Hollywood movies, there is enough technology out there to make things really look real. We don't need more realism in that aspect, and we don't need even better water representation. What we really need is we need to automatically find all the water so we can make it look like that. And we need to find out where are all those trees and what type they are so we can really render them that way. So there's other issues like time of day and seasonal rendering, which would require us to remove shadows to understand what surfaces we are having here. What's a window? Where will be a light turn on and shine through in the middle of the night? That's, again, you're sensing a pattern here. We need to have a good understanding of what we are looking at, what the software is dealing with, what the tools are applied to. Optimizing for our online web-based applications means, I said it earlier, lower footprint, better transmission or download speed, which again requires better. We want to get higher and higher fidelity textures and other features through to the client. We need to do better and better job compressing data, using level of detail, being smart about how we size it up and reformat so it goes through that pipe quicker. Again, there's these issues with sensitive content, offensive content, especially dealing with user-contributed content. We had to eliminate imagery from our databases for the most obnoxious content. People had the idea that spray paint on the grass, big whatever obscene things, will be really, it's like high school pranks. We'll make them local celebrities, and of course that shows up in the early imagery, and we had to take it out. And typically we didn't find it, the press finds it, or the bloggers. So happened with the not so nice thing was the propeller of the nuclear submarine that was absolutely not supposed to be in the imagery happened. So detecting such things that are not supposed to be in images, again, required to understand what is it that I'm actually looking at. Language support is another thing. Yeah, you showed good stuff at the Tech Fest about finding letters and writing in different languages in imagery. Wouldn't it be nice to actually then replace it with the local language that the user is has for his settings when he signed in? So again, understanding what we're looking at, this is a common theme here. So with the application support, wouldn't it be nice to enable functionality like pointing at a random object in that virtual world and say, what is it? Who lives there? What is in there? What is it made of? Since when does it exist? Boy, did I like that time slider thing today. That's very interesting. What's playing in that theater? Can I have a preview? I mean, there's a lot of things that we can conceptually think as really cool applications, but again, all of those would require that we have some built-in knowledge that tells us more about what we're looking at, not just the shape of it and how big it is and where it is. So in a nutshell, what I'm saying, remember that one slide where I said this is where we are? If we don't start getting more semantics, more thorough understanding of the databases we're dealing with into our algorithms and in the ways we're going about creating those virtual worlds, we will have a hard time to jump across this line here without having a huge cost in manpower and manual labor and so forth. So that is a real challenge for us, everyone out there who wants to build something at this scale with this functionality. And I encourage everyone here to do some creative thinking because, boy, we need it. So what I'm saying, what I'm coining here is we need smart models. And at the minimum, we need to know for each object in those 3D models in these databases, we need to know what it is we're looking at. As at least a basic type. It's a building, it's a tree, it's water, it's bare earth, something like that. And it would be even nicer to have more a specific tag for it. Specificity, okay. Like, this is actually a gas station. This is a restaurant, this is a hotel, this is a fur, a whatever. Surface material. Would that be nice? If we would know this is glass, we could make it reflective. If we know this is brick, we can make it a little bump map and render it differently. Well, and for one thing, we could actually start replicating, right? So, because for a brick building, all you need is one brick, and then you replicate it. That would be a nice compression. Well, I'm sure by now you have read all that, so I save you me reading it for you. But on the very end, I have two things here that those come in from the practical world again. Owner and copyright holder and use restrictions. Especially if we start combining data that come from different sources, maybe from a catalog, a warehouse, or user contributed. Some people might restrict it and say, hey, I don't want you to use that commercially or outside this country or I don't know what. So that's also a very important attribution for us that we need to take care of. Another example is like, do not use it in broadcast, right? It was done by one movie studio. They don't want to have some other movie studio use it. So conclusions. We have solved a lot of the theoretical issues, but for the practical implementation of doing these things at very large scale, very cost efficiently, because that's the only way we can do it at such a large scale, we need to focus on a couple of those practical implications. So in the real world, we're facing copyright issues and obscenities and language barriers and all these things, and we need to take care of that in our tools, and we need to do some creative thinking getting there. So adding semantics to the 3D models is going to be the big next challenge. And without that, I'm stating the 3D web is going to remain this mirage at the horizon there, and we can get closer, but we will never reach it. And we're going to be stuck in that world that's nice to look at. We can mesh up, but eventually it gets pretty much boring once you have looked at everything, because you can't really do a whole lot with it without enabling these functions I talked about. Guess that's it. Yes, it is.
Questions?
Okay. Yeah.
Are you going to be looking at automating metadata collection? Because if you take Tally Atlas, for instance, they've got 500 people in India looking at time-elapse photography, creating metadata, things like speed limits, signs, lay-bys, where the litter bins are on the roads, all that. Are you looking at automating that collection?
I would actually turn this question to the room and said, if someone wants to work on it, actually, I think some people are actually going to talk about this hopefully tomorrow. But that's a huge problem, right? I mean, take OCR and just try to apply it to the entire world. And it's not only text, right? It's everything else.
Yeah.
So
OCR is a good example, right? So yes, clearly the answer is whatever can be automated, we're going to try very hard to automate. And where there are practical limits, we need to look for different options. But yes.
Other questions? There will be a demo. Yeah. Please.
Okay, I think you had a long list of things to do. Is there any prioritization? I mean, do you think which one is more important? Or
no, actually, this is really a laundry list of, hey, there's a lot of unsolved problems out there, or that there might be solutions, but it's the type of solution that worked once, right? And someone quickly wrote a paper, and here it is, under lab conditions, but applied to real-world scenarios, it might break down. So some of those problems look, on first glance, hey, that's solved. We've done that. But what I'm saying is when you put it in the context of what we're trying to do here and at the scale at which we're trying to do it, with the sources available and the resources available, you're hitting limits very rapidly. And so there's a lot of optimization still possible, and every little bit helps. So I don't want to prioritize here too much. Jason can talk about that when he talks about his stuff.
There is an interesting question. If you solve problem A and suddenly B becomes that much easier, and just understanding sort of the dependencies here and what fusion you can then leverage later is interesting. I think that's actually a research question. I mean, it's hard to guess what's going to help you in which sequence. Yes, please.
Hi, Wolfgang. In one of your slides, you mentioned about the quality of an object.
Yeah.
Can you please talk more about it? Is there any current algorithm to assess the quality of the objects? How do you select?
Well, it's very basic, right? You can go about it very statistically. Say, hey, I'm looking at a building and it's 7 kilometers tall. Something's wrong here, right? So you can use some basic heuristics about what am I supposed to see here, and what's the shape and form and size and color, and what's its spatial distribution amongst its peers, right? If I have a city, I typically have 1 to 3 airports. If I suddenly have 72, I have a problem, right? So what I mean is just our intrinsic knowledge about how things should look and where they should be and how they should be correlated to each other helps a little bit. But to measure it, the whole question about what's the quality, right? We have endless discussions about what's shippable quality. At which point can we release it to the public? And what are the measures? And then you say, I have 10 examples of really good buildings. And then you get building number 11 and it just doesn't look like any of the 10. So back to if I would have these measures, like do I know its basic shape, type? Do I know its specific type? Do I know its surface characteristics? And what's the confidence level with which I have determined all these characteristics? Would help a lot to then compare two renditions of the same thing or similar things and say I can always form some vector and weigh it, and then make a comparison. But again, it's an open field for discussion and research.
To add to that, I mean, definitely a sort of heuristic based approach that all buildings in the city tends to look like X, and this is an outlier. Is sort of the naive solution. The question Hanan mentioned on gazetteers before. It's interesting if it's possible to develop a generalized gazetteer of building, objects or building parameters or building sort of primitives or architectural primitives. And said, yeah, this actually has the right set of hierarchical constraints that make it behave like a building. And yeah, you'll have outliers, which are more complex buildings, but it's probably very few of them that are more organic, right?
And what you said earlier, one thing might make the other thing better, right? So we find all the streets and the street names automatically, and we know that most buildings have some street access, right? So now you can start matching the roads with the buildings and to say, okay, they need to have street access. And, well, then we count the buildings and we have a database that has all the known addresses. And we say, okay, this piece of street should have so many addresses. Do we have that many buildings? I mean, there's a lot of, you need to look at the problem at a very global level and see how we can piece it all together from many different sources. That's most likely much more promising than trying to focus on one data set and one source and try to solve all the ambiguities within that one data set.
Any other questions? We'll have a chance, of course, to talk over dinner. If not, thank you.
Thanks.